Welcome. Today we're going to be talking about stormwater management design. We're going to be looking at our site layout. We'll talk about hydraulic conditions and the water quality design standards that we'll be using for our design project. So let's get started. When we're talking about site layout, we have to think of a couple of things. We have to think of what is the proposed elevation of the ground going to be and what is the existing elevation of the ground going to be. And specifically, where do we want the runoff or the drainage to go for our project? Prior to the hydrologic and hydraulic analysis of the design project, we need to evaluate the site with respect to the purpose of the project we are designing. For example, if it's a subdivision, we have to lay out our roadways, individual lots, and the location of our stormwater management facilities. Therefore, it is important to remember that every site layout requires the designer to think in 3 dimensions. And in other words, one should not lose sight of the fact that the elevations vary across the site, and the vertical component of the design must be considered when developing the horizontal site geometry, such as the roads and where the houses are going. Typically, we try to place the stormwater management pond at the lowest point of the site. However, sometimes the client or developer has other ideas on how the site should be laid out. And oftentimes, this becomes an iterative process when conceptual layout is refined based on existing and proposed site elevations that must be taken into consideration. Part of this refinement can be accomplished by using computer-aided drafting software packages such as Autodesk Civil 3D and the MicroStation program. The emphasis on vertical and 3-dimensional thinking during preliminary site layout is due to the large part of the increasing importance of drainage and stormwater management considerations. Site layout, grading, and drainage are interrelated. Stormwater management systems are integral parts of a functional site and require early attention in order to ensure sufficient space is allotted for the pond locations and adequate outfall scenarios are assessed. We have to understand where the ponds will discharge to, whether that be into a stream, wetland, or even an existing stormwater management system. In order to develop a comprehensive stormwater management system, one that meets applicable jurisdictional guidelines for water quality and quantity, in addition to adheres to the developer's expectations and project goals, you must have a thorough understanding of the site's hydrologic conditions. The hydrologic conditions of a site, the topography, soil, land cover condition, and rainfall pattern are assessed pre- and post-development and compared. This comparison determines the applicable stormwater management requirements and reveals feasible strategies for managing the site runoff. Like all components of the design process, the hydraulic analysis is often iterative, especially when it comes to assessing the post-development scenario. Watch as this site goes from the pre-development conditions to the post-development conditions over the span of 20 years. Like every rainfall event is unique, so are all project sites, and the resulting runoff from a storm event is also different for each site. Surface conditions such as the amount of vegetation, land use, soil type, and topography affect the volume and distribution of runoff. When designing an individual component of a storm drain system, the effects of the temporal and spatial distribution of runoff have little impact. However, the effects must be considered when designing larger components such as the stormwater management facilities or our storm ponds, major culverts, or determining the floodplain. Take note of the green areas that stay consistent throughout the years in these pictures. The green areas to the west and south are wetlands and contain a majority of the floodplain for this area. To the east is the Lake Toho in Kissimmee, Florida. Because hydraulic data is historic by nature and unlike conventional experiments where data is collected through repetition, hydrologic data is collected through observation of an event. For example, how much water is measured for rainfall for a storm or the floodwater depth in a floodplain. The variables relating to the hydrologic data, such as time and space variation of a rainfall, abstractions, surface conditions, and numerous others that affect runoff, are considered continuous variables. That is quantitatively, they can be assumed at any real value. But because of the combination of these values and all such variables are infinite, the exact repeating occurrence of an event, though not impossible, is highly unlikely. The infinite number of possible rainfall and runoff events present an improbable task of ever obtaining all of the unique data potentially available in the hopes of predicting hydrologic events precisely and accurately. Therefore, statistical generalizations are used to represent design storm events, and probability analysis is used to predict the likelihood of the occurrence. That's why we have our design storms, our 1024s, our 10-year 72s, etc., to determine and give us a specific design for the designing ability. This is the data that we will need to use to design projects such as the one you are seeing in these pictures. To go in a little bit more detail about stormwater management design, we need to take a look at a couple of things on our site. So this is an example of a parking lot. Over here you have the detention pond. So all the water in the parking lot drains to a couple of the inlets and then goes to the detention pond. There is a building here and the roof goes to the detention pond also. These dashed lines represent pipes under the ground. You also see an NP here. NP stands for normal pool. Sometimes we use CW, control water elevation, CWE. On this it says normal pool has an elevation of 832.3 and the 100-year storm event stages up into this pond 836.32, almost, well, it's over 4 feet, just a little bit over 4 feet. It says surface to pond, how many acres, and the curve number is 98. So all of these inlets, and you can see these numbers here represent the elevation of the ground. So we can see what how much water is actually going to this detention pond. All these little lines here represent the elevation of the ground. These dots, or these elevations here, represent what the ground looks like on the outside. You always have to remember you have to tie into your property. So let's take a look at the next slide. Over here we have another commercial site, and what we have here, our parking lot, we have the dashed lines represent existing ground, whereas the solid lines or contours represent proposed. And you can see how we're always tying into the edge of our property. It is extremely important that you always tie back down into grade. There is an existing swale over here, and you can see this is a mitered end section that goes to some type of a head wall here. This is a bioswale, so they're doing a more an LID, low impact development for this project. You can also see here that these arrows, so I have a contour here that drains and then it goes to a 97. Here's the contour here and it goes to a 98. So I know that the water's draining this direction, and they're telling me it's 3.5%. Same with here. So the site all drains back to this bioswale over here. Now, you can only allow off your property a certain amount, or you can only let off the right of way. So notice there's a ridge right here. There's a high point. So they're sending water off into the roadway over here and off into the roadway over here in their driveway, but they can only send what is from the property line, and that's this line right here that you're seeing. Again, you can see the tie-in of the existing grades. We also have a rain garden, which is another a low impact development. You can see we've got elevations throughout this site. So this site's got a lot more asphalt on it than what our normal subdivision design is. But notice right here it says porous concrete parking lot. Because it's porous pavement, they can actually reduce the curve number down. So if the curve number was 98 for true asphalt, then the porous pavement or porous concrete can be something a little bit lower, maybe a 90 or an 85, depending on the material. So let's take a look at the next one. Over here we've got inlets, and you can see a high point. It says sheet to drain, and you can see the arrows. So these are contours. Everything is going outward away from this ridge. And we also down here in the blue is a stormwater pond. So all these inlets collect the water, and then these blue lines represent the piping. So this is our site layout and our grading plan. So this is how we design, we start to think about it. Now, these pipes are for designing the actual inlets. What we have to do first is we're going to take an overall area to figure out what size that pond needs to be. So we'll be using curve numbers, time of concentrations, and area to figure out the volume that we need for these ponds. When we go to do the design of the inlets and the pipes, we'll actually be using a different equation. We'll be using the rationale equation, and we're going to be using a runoff method, or a runoff coefficient, which is similar to the curve number in the idea that it's based on land use. All right, so here's another example. It's a little bit clearer. You can always see, again, our existing contours are going to be in dashed lines, and our proposed grades, our proposed contour is going to be in solid lines. Here we've got maybe it's a a parking lot that's being redone, but you can see where we've got proposed grades and we've got inlets that are supposed to be set. So this is the type of site plan that we'll be working on. So we'll have to figure out, it says, even up here it says 97 square feet of additional impervious area. So we have to account for all the little impervious that we add to a site or even take away from a site. All right. So the next thing we need to talk about is the water quality design standards. So I'm going to go back a couple. So we have to figure out how big this pond is, and we have to figure out the control structure that allows us to permit a pre and post development and discharge and provide water quality. So the water quality design standards that we'll be looking at, since it's St. Johns River Water Management District, I've given you a hyperlink here. We'll take a look at the ERP. Now here's where I go to the ERP, and you can download these two documents. The handbook basically tells you all of the parameters that you have to design by. And the other one is just kind of like a manual on is all the specific design requirements. So on the first one is for the handbook, and the second hyperlink is for the permitting information. I clicked on the permitting information. This is what I come up with. Here's again the document and the hyperlinks. We'll be using the parts 3, 4, and 5. We'll be looking at water quantity, quality. The part 4 we don't really do a whole lot with because it's design standards as in maximum allowable limits, and usually we look at it as a pollution. If we have to get to the point of determining how much total dissolved solids and that type of thing, we usually send off to a water quality specialist. So we look at best management practice to say that if we build a certain design pond, then we know that we're going to meet state water quality standards. So technically we'll be looking at 3 and 5. So here's part 3. If you look at it, we basically see that we have to meet the annual peak discharge for pre and post, and we can't have more than that. There's other bits of information that we have to follow by, but in general, we have the mean annual that we have to abide by, pre and post peak development. We have the post-peak development discharge rate can't exceed pre-development for the 25-24 year storm event. And they have specific things where if it's discharging to a certain waterway, it has to be even maybe even more stringent criteria. And then we have the post-development runoff for a 25-year 96-hour. So we're looking at, and that's for systems that are landlocked. We don't have technically a landlocked basin because we can probably discharge off to, on our design project, off to the north to Lake McCoy. I believe that's what the name of it was. Now the next one is the water quality standards that we're actually going to be looking at. Is we could do a wet detention design, but APOPCA said that they wanted us to do a dry detention. So we'll be looking at sections 12 of the best management practice. In section 12 it says here's the treatment volume. It says if we're doing an offline detention, you must provide at least the first 1 inch of runoff or 2.5 inches of runoff from the impervious area, whichever is greater. That means we have to look at excuse me, how much impervious of the site we have, or we're going to multiply 1 inch over our total area and have to provide that volume within our pond. Dry detention removes less pollutants on a per unit basis than other traditional best management practice. Therefore, dry detentions must treat a greater amount of volume. So we have to provide either the first inch of runoff or 2.5 inches of the impervious area, depending on whichever is greater. And I'll show you how to calculate that further into class. The second thing is recovery time. It says the outfall structure shall be designed to draw down 1/2 of the required treatment volume specified above between 24 and 30 hours. That means it has to withdraw, it has to pull the water elevation down in the pond within 24 to 30 hours so that if another storm comes in, then it has the availability. Now the next part says the outlet structure. The outlet structure shall include a drawdown device, and a drawdown device is usually a hole in a concrete box or a V-notch weir, which allows sets to slowly release the treatment volume. And there are schematics that they use you can do for design aids. In addition, the structure must include a device to prevent discharge of accumulated sediment, minimize exit velocity, and prevent clogging. So the device for minimizing accumulated sediment might be a trash barrier on the upstream end, or some type of device on the downstream end. Minimizing velocity is usually some type of riprap, and prevent clogging. The clogging is going to be your trash racks or skimmers. All right. There's also examples of this in the in this manual. So as we go throughout the semester, we'll be taking a look at those. All right. I'm going to go ahead and pause here, and then we'll get started on the next section. All right.